Try to look at some of these actual life applicable things. So the first one we'll look at is the idea of increasing sales. We kind of did this earlier, and so we looked at that idea of like companies that advertise. That first time they get that advertisement out there, what's it kind of look like? It's our viewers and our sales and stuff increases pretty fast, right? And then it starts to taper off. We saw that with YouTube videos as well. We had the exponential growth early, but as people had seen a lot of it, it started to fade off, and it kind of had this logarithmic kind of fade out. Okay? So we're going to look at the same concept with this increasing sales. The specific is we're going to look at a manufacturer of small storage buildings. So they're going to look for these small units. And they think that they can sell 40 units per month. That's going to be their maximum. Now, after increasing their advertising budget and enlarging the sales force, we're going to expect to grow according to this model, okay, where S is the expected number of sales and T is the number of months, so it's over time. So how many sales were being made prior to the expansion? What can we do to try to help figure that out? So we think about our two variables. What is S? Our sales, good. So the number of sales, that S of T. What is T? Time in months, good. So I want to know prior to the expansion how many sales I made. What do we want to do? Good. So at the time we start, prior to doing anything, time is 0. Let's go ahead and plug that in. So we end up with our equation, okay, our S of 0 before we do anything. 40 over this 1 plus 1.5 e to the negative 0.08. T is now 0. So this turns into 1.5 times e to the 0. Yes, Barry?
Do you have to create a graph to solve it?
No, I'm just kind of showing us a visual of how this is looking.
Okay.
Just a rough guess. Okay, so we got 40 over 1 plus, what's e to the 0? 1. So we just have 1 plus 1.5, which is 40 over 2.5, which is 16. Good. Okay, so what does that tell me? So
0 months, you have 16
units sold. Good. So before we even started our ad campaign, we were selling 16 units per month. That's what we're working on. Excellent. Okay, that's also kind of like our y-intercept, right? That 0 time, where we started. Okay. Next, we're going to take a look at is I want to try to actually expand this thing. We want to figure out how long it's going to take us to do that. So I've got this equation, and I want to know how long is it going to take me to get to 25 units. Okay, now what should we do? For our S now. Excellent. So we're going to have 25 units is how many we want to sell. Equals our 40 over our 1 plus the 1.5 e to our negative 0.08 t. Okay, our variables in the denominator, how do we undo that? We're going to multiply by the denominator. Perfect. So we'll end up with this 25 times the quantity of 1 plus 1.5 e to the negative 0.08 t. That should equal our 40. Okay, now what can we do? We could. I'm gonna go a slightly different route. But we could divide by 25. We could distribute. Okay, so when we distribute this through, we end up with 25 plus 37.5 e to the negative 0.8t, 0.8t equals our 40. And then we can start to get our variable isolated, right? It's attached to this e. So let's subtract 25. 37.5 e to our negative 0.08t. So it's going to equal 15. Then we can divide by this 37.5. So we get our e to the negative 0.08 t equals 15 over 37.5. Okay, now we're in the exponential form. How do we undo E, Henry?
So you need to take the natural log
Good. Since we're working with that E.
and put natural log to be 15 over 37.5 out.
Good. So when we take the natural log of both sides here, we're going to end up with that 0.08t that moves itself out front. Natural log of E is 1, so that goes away. And then we have the natural log of our 15 over 37.5. Last step then would be divide by that negative. So we get our natural log of 15 over 37.5 all over negative 0.08. And that turns into a decimal approximation for us. Okay? I believe our time ends up being about 11 point something. 4.8. Cool. All right. So in about 11 and a half months. 2.9. 4.29. 2.85. Anyways, it's 11 point something, right? So after that 11th month, going into almost a full year of doing this ad campaign, we should expect to finally get to our 25 units sold. Okay, it's going to take us much longer to eventually finally fill all 40 of these bins and reach our capacity. And so that starts to work into that piece. Okay, how are we feeling there? Okay, so you're going to take that equation, you're going to work through it, but very similar to the stuff we've been doing in the past. Okay. Next one we're going to take a look at is going to be depreciation and appreciation. How many of us have families that own any sort of a company that's got like trucks or something in it that depreciate over time? Okay. Like my dad, they have a construction company, so like their dump trucks, they depreciate over time. So that's one of those things they can use as a tax write-off. So how about homes? What usually happens with homes? Homes usually appreciate, right? So the longer you own a home, typically, as long as you're upkeeping it and you're doing some of those things to it, the value of your house typically grows over time. Okay, so that's the appreciation side of it. Okay, how many of us own a car right now? Okay. Is your car worth more today or next year? Today. Okay, so again, there's another idea, that depreciation of value, right? So over time, cars start to lose their value. Okay? Which one do you guys want me to do as an example? Do you want to do appreciation or depreciation? Depreciation? Okay, so let's take a look at 55 then. Okay, 55 is the car. We've got this formula. Time is going to equal some given constant, and again, this is one of those things you'd find with some actual field experience and looking at past data and figure out what the depreciation values are. Okay? That's just a constant, they'll give that to us. The V sub n is going to be our value when it's new, so that's kind of like your present value. The V sub f is going to be that future value, so what it's worth in the future. And then we're going to want to go figure out how much this car is worth. So we've got 3 years from now, we want to know how much this car is going to be worth. The K value they'll give us is 5. So in 3 years, T equals 3. Given a constant depreciation rate of 5, we'll have the natural log of, purple screen. I don't know why my mouse thing is totally tweaking today. All right, there we go. And so our new value is 28,500. And we want to know what the future value is, so that's still our unknown. Okay. So in this particular case, our variable is inside the log, so let's isolate it. We can divide by 5. So 3 divided by 5 equals our natural log. How do we undo a natural log? Go from logarithmic into exponential. What's going to be the base of that exponent? e, because we're dealing with natural log. Good. So we're going to end up with that e to the 3/5 equals our 28,500 divided by our future value. Okay, how do we get future value by itself? Let's multiply by that, and then let's divide by the e. So our future value is going to equal to 28,000. Divided by our e to the 3/5, which that's just the value. What do we end up with? Everybody got that? 15,641. Perfect. What if you type something in and all of a sudden the car value turned into 32,000? You'd be like, I did something wrong. This should not be worth more, right? The understanding, our expectation is this is depreciating. We should have this negative value. Okay, this deep, not a negative value, but a depreciation. Should go down in value.
Drive it and add a whole bunch of
You could, but then you're changing the initial value of the car too, because you're adding more money to it. So that makes it a little bit more complicated, but good.
if you got it all for free.
Good idea. Then you got some really cool friends or something. All right. So there's the depreciation. The home one's also, my favorite part about the home one, you guys read what the question is for 56 that you guys have to answer? They're definitely not hanging out in this part of town, right? It says, if a new home in an upscale neighborhood is purchased for $130,000, yeah, maybe Arizona, and I don't even know if that's in the upscale part of town, is it? Yeah, my buddy in Kansas just bought a house for $130,000. It's a nice house, but it's 35 minutes from Kansas City, and there's nothing else around him. So, I mean, if we got an upscale neighborhood home around here, we'd have to add a zero to that, maybe 1.3 million, right? So, I mean, we got some pretty nice houses around here, probably in the 600,000 to 700,000s too, but definitely not 130. That'd be nice. So. Anyways, on block day, we're actually going to have kind of a fun project. I'm going to have you guys take the computers and go find your dream house that you want to buy. And then we're going to figure out the mortgage for it. And then we're going to work backwards and figure out how much of a salary you or even you and a partner would need to make combined to own that particular house. It's kind of fun to look at. Then we'll go the other route. We'll see, okay, what do you actually want to do with your life and how much you can expect to make doing that. And then we'll figure out how much of a house you'll be able to afford 5 years out of school or 5 years into that job. That's also kind of a fun one. Okay. Okay. Now we get to stretch your brains a bit. Some of us have been like, hey, logarithms, that's what I got last year. I'm feeling good with it. We're going to take this one step further. You know all those questions at the end of the chapter that say extending the concept that we usually don't do? We're going to do it today. I'm going to stretch your brain a little bit, make it hurt. Because we're going to play a game today, so now we're going to have some challenges. We're going to do 64. 63 is your homework. But it's very, very similar. What's our hint? Note that the equations in exercise 63 and 64 are in quadratic form. What does that mean? It means we could use the quadratic equation, or we might even be able to factor it. Okay? So, here's going to be the hint. You guys can do 63, but just kind of follow along with what I'm trying to do on 64 here. Okay? So, 63, I can rewrite this as 3 times e to the x squared. Anybody know why? Do we agree? But why? Chris? Perfect. Good. So we got powers of powers here, so that turns into that 2x. Excellent. Thank you, Chris. So then we have this minus 4e to the x, minus 7, but we're going to add that 3 over, so this will be minus 4 equals 0. Okay? That still looks kind of ugly, right? We're like, oh, what if I did this, though? And I just changed it into something that looked like that. Does that look nicer for you?
Yeah.
What did I do? We substitute. Good. Catherine, what did I substitute? We said that e to the x is just going to equal n. Okay? That's totally legit substitution. You can do that. Okay? Makes life look a little bit easier. So now what we can do is let's just treat that like we would a normal quadratic. How do we factor something like that? When I go ahead, we have a coefficient of something other than 1, so we need to find the AC. Good. So my AC, we're going to multiply this 3 times the negative 4. We'll end up with negative 12. What will multiply to negative 12 but add to the negative 4? What are the factors of 12 that will subtract into 4? 6 and 2. Good. So we'll have a negative 6 and a positive 2. Okay. We're going to use that, substitute back in so we can actually solve this thing out. So we'll have 3n squared minus 6n plus 2n. So all we did was we took our b and split it into 2 parts. Still the exact same equation. Minus the 4 equals 0. And then here's that thing where we build our imaginary wall and factor by groups. So we have a 3 and an n out front. We'd be left with an n minus 2. Second group, we can pull out a positive 2. We'd be left with an n minus 2. We know we've done it correctly because the insides match each other, right? So that becomes one of our factors. That's our common term. So n minus 2 gets factored out. And we would be left with 3n minus 2. So let's pretend this is all we needed to solve. What would my two solutions be? N equals 2 and... Oh, that is positive 2. Thank you, Elliot. Okay. So n equals 2 and negative 2/3. So all we were doing there, right, is you set each of these parentheses equal to 0. So now what do you think you need to do to actually solve for x? We need to substitute back in. So now you've got this first one, which gives us e to the x minus 2 equals 0. Or we've got 3 times e to the x plus 2 equals 0. Okay. Now we just solve for both those. So for the blue one here, we'll add 2 over. E to the x will equal 2. How do we undo e to the x? Take the natural log of both sides. So x is going to equal the natural log of 2. Good. That's a number. We can get a decimal approximation. Okay, for the green one, similar idea. We'll subtract 2. We'll divide by 3. And then we'll take the natural log. So what is the natural log of negative 2/3? Somebody give me a decimal approximation. Type that in the calculator. What happens? Error, error, error. Why? Perfect. We cannot take a log of a negative. So this solution is not real. We can't have that. The only thing that will be a solution in this particular case is x equals the natural log of 2. Okay, you saw that a little bit last night also, where you had a couple things that either were non-real solutions or you ended up with extraneous situations because we were taking logs of non-real solutions. Okay. Good. All right, how's our brain feeling on that one? So that one we stretched a little bit, right? Concept was, let's try to convert this into a quadratic. Let's make it look a little more familiar to us, and then we can work through all the properties we understand, and we'll try to work back with how to find x. Okay? Last one we got today. Also going to stretch your brain just a little bit. I'll let you guys choose which one we do here. We're going to prove that statements are true. So in this particular case, you've got the choice of A or B. Which one do you want me to do? B. I didn't even look at B. Please do B. Okay, typically B is a little bit harder, right? Okay, so let's think about this one. I want to show that B to the x equals e to the rx, where r is the natural log of b. Okay, a lot of letters, right? So that's kind of ugly looking. What did we do, though, with that same trait that Chris was telling us about? What might be able to help me here? I've got a b to the x. How can I get something over here to the x? Maddie, what would you do? Kaylee, what would you do? What does multiplying exponents allow me to do? We can move them around a little bit. Where can I move this? Joey, what would you do? That's good. So that idea, right, Chris? Restate what you told us. Multiplying exponents is the same as the powers of powers idea, right? So we can take this and basically make it to the x now, right? Basically kind of raise it to the x power. How can we get the x out front now? This goes back to something we're a little bit more familiar with. How do we move an exponent? You need to take the log. In this case, let's do natural log. So we're working with e's. So this could turn into x natural log of b. Okay? Because that allows us to move the exponents out front. Then this will end up being x times the natural log of e to the natural log of b. And then what's one of those properties we have with natural logs, or logs in general? What are we able to do with the exponents inside of a log? We can move them out in front, right? So this can get moved. And so we'll end up with this natural log, or x times our natural log of b, equals x times, we're going to move this, times the natural log of b, which leaves us times natural log of e. What is the natural log of e? 1. What do we get? True statement. Boom. Proved it. Okay? So we're going to take a little bit of that brain power and stretch it just a touch.